So first of all, thank you for the introduction, and I'm very much convinced that this overcoming the Markovian, for instance, the Markovian paradigm is one of the next things on the schedule for the nearer future. But however, I would just like to point out here that even in the Markovian case, we get into very different situations. If we, for instance, look at a process I will briefly look at later, but one could think, for instance, of reinforcing processes like Polya urns, which we also looked into in the past, and I will just mention it briefly in the beginning, where this basically also this equivalence between ensemble and time averages becomes very crucial, and because most of the times you see a winner takes all kind of dynamics in the time domain, but only once you look at how often somebody wins, then you get more or less the ensemble average. So there's already a lot of tricky business in the Markov range of processes that we could look into. However, today I would like to mainly look into not per se stochastic thermodynamics. I would basically be interested a lot how what we are doing here connects to, or can be nicely connected to stochastic thermodynamics. What we do is basically what Boltzmann already did. We look at Boltzmann entropy, basically log multiplicity, and ask ourselves what happens if we apply this entropy concept to different types of processes. And the result is actually for some processes we could find, I think, quite nice results. So what are we looking at? We are looking at some process X where we take some samples where each of these xi's is maybe now an ensemble, but it also may be in time. We can make they are elements of some sample space omega, and what we can do now is we look at the histogram K of how often did one of these states occur in our sample. So we have n observations, we have the histogram K, and then we have here P, the relative frequencies with which we observe now the different possible states that these xi's can take. And depending on which process we are looking at, we get, of course, now some probability P of K, the probability P that we observe some histogram K, depending on parameters which parameterize the process. In normal multinomial processes, this would be the Qi, so this would be the probability distribution from which we sample, basically. And so what we can ask now is what do we require so that to have a log multiplicity? What we require is that this probability factorizes in a multiplicity factor. How often can we, in how many ways can we observe the histogram K in terms of sequences, and which realize this K, and what is the probability to observe a particular sequence. So in independent sampling, the multiplicity, we know the multiplicity, it's the multinomial factor, and this would simply be product Qi to the power Ki. This would simply be the the probability to observe a particular sequence. And then if such a factorization is possible, we can normalize with some suitable factor, and typically this would be a constant. In physics, it would be the Boltzmann constant. In information theory, this would be something like 1 over log 2, as, depending on which base we try to, which base we use to represent our information, and then 1 over the degrees of freedom. So in our sequence here, the degrees of freedom basically would be n. Okay, so this is simply a very brief recap how we can go now from Boltzmann entropy to the Shannon entropy form. And this is basically, we take the multinomial factor, then we apply Stirling's formula, and in 3 lines you see that log of the multinomial factor divided by n simply is now sum over the allowed states I pi log pi minus. Similarly, for the sequence probability, we simply get the cross entropy pq is sum over I minus p log qi, and both together give the well-known expression that the Kullback-Leibler divergence is cross entropy minus Shannon entropy. And so this works fine for independent sampling, so for IID processes. And just a quick remark maybe here, if we now, for instance, reparameterize our distribution function in terms of a Boltzmann factor, and we insert this in the cross entropy term, then we see that the cross entropy basically gives us what we have in the maximum entropy principle in terms of Lagrange multipliers. We have here the normalization constraint, and we have the energy constraint. And of course, the well-known maximum configuration solution for what do we do? What do we want to do? Maybe look at here. What we want to do is we want to find the most likely histogram, given we have made n observations, and so we always maximize this. In fact, we are minimizing relative entropy, or we are minimizing Kullback-Leibler divergence in this case. And what we see is we can estimate the distribution function we sample from with the observed relative frequencies. Well, so the question that arises now is, can we in a reasonable way extend Boltzmann entropy to other process classes, and does this work? And in fact, we did this for let's say a very simple model of a driven dissipative system. Think of this staircase here as energy states, and the ball that is jumping down would be now, let's say, the dissipative, the energy state of the system. And while it dissipates energy into the energy sink, it always can select any of the energies below its current energy state. It cannot jump up. However, if we couple the system to a hot bath or an energy source, we can have movements in the opposite direction, so that even though this part of the process would not be ergodic, we somehow re-establish something like ergodicity, but not equilibrium type of ergodicity, but simply we are running through the stochastic cycles. So this would be one example where this generalization of Boltzmann's, or not, we just use Boltzmann and apply it there, works. But what we will look more closely in today is structure forming systems. So what happens if we have something like molecules that cannot only exist in their singular state, but they can bind to each other, and so we get the in fact phase-based growth that, unlike, let's say here, these independent sampling processes, they all grow, they have exponentially growing phase space. But in fact, if we look at this type of systems, we may find a super exponentially growing phase space. And if we look at systems with internal constraints, then we can in fact find sub-exponential phase space growth. This particular system has an exponential phase space growth, but not w to the power n, but something smaller. So the basis of the exponent is reduced in this case. Well, so just in one flash here, because I don't want to stick here, is just to see if you go down the staircase, you can actually you see that this, if you think about it for a while, or then one sees that actually the multiplicity factor of how many sequences would realize actually the same histogram, one sees that this is a product of binomial factors in this case. And so what we can do is we can do the same thing. We determine the multiplicity, we determine the sequence probability, take the log, divide by the degrees of freedom, and then we see our entropy here has here a term that still looks very much like Shannon entropy, but we get these additional terms here. And in fact, the cross entropy also has this known term with Qi is now the width of the stair, so to say, and the big Q is the cumulative distribution function here. Then we get this additional term here also in the cross entropy. But if again we minimize the divergence, so cross entropy minus entropy, in this case, then what we find is that the maximum configuration solution actually predicts this distribution function, which is no longer exponential, but in most cases, or for many choices of Qi, one sees that this is basically Zipf law. So what we reproduce is a power law here in the visiting distribution of the systems to the different states. And in fact, one could also do thermodynamics, and what we see here is one could look at what is free energy. F is U minus Ts, and there one already would see a problem that it's not so clear what free energy is here anymore. So is it so? But well, this is maybe a discussion that I skip here, and go now to exemplify this possibility to use Boltzmann to use Boltzmann to predict Boltzmann entropy to predict distribution functions for systems that are not equilibrium systems in that sense, and that are not in this case, we would have a trivial non-equilibrium system, in fact, and with no detailed balance. So there is no detailed balance in the system. There is a circular current actually running here. Anyway, so how does this work with structure forming systems? So if we need to consider molecules, and to our surprise, actually. So it was inspired by some work from Henrik Jensen on magnetic coins. So where you have coins that not only have up spin and down spin or head or tails, but also can stick together. So we have sticky coins in a way that where this sticky this bound state actually is an additional way of different additional configurations the system is allowed in. And so we could have now for each of these bound states, so 1, 2, 3, we could have a number of states, 1 to mj. Mj always needs to be smaller than the total number allowed, and then what we can do is we get now a different kind of normalization condition if we assume that the total number of particles here is conserved. So because this molecule has 2 particles, so if we count the number of these molecules, we have to multiply with this factor to get to the original number of atoms, actually. And to our surprise, actually, already Boltzmann did something very, very similar in 1871. The only thing he was really still computing totally in terms of multiplicities. Well, so in order to compute what we would call Boltzmann entropy here, so log multiplicity again, we would have to find now we have to consider find out what is this multiplicity factor that we are looking at. And if we think of molecules that simply have this rather simple structural states that it can obtain, then we see that, for instance, for a J, for molecules with, if we only look at molecules with J atoms, then the number of different configurations that would lead to the same indistinguishable state would in fact be this factor. So the number of molecules to the factorial, because we can here exchange the molecules under with each other, and then of course we can exchange the atoms within the molecule, and then we need to take this factor again to the power required here. So with this done, we can write the multiplicity factor as now very similar to the multinomial factor, but slightly different with the associated relative frequencies here, number of molecules divided by the total number of atoms that we allow here. And if we compute now this Boltzmann entropy, which simply is log W here, we get this expression. So if we go from here to now we do something that actually Boltzmann did already in 1970. He says, well, if we have the atoms flying around in our box, we subdivide our box into smaller boxes, and we will consider only things to be allowed to be molecules if they are close to each other. And with such a density constraint and computing the reduced entropy, so the entropy per atom in this case, would lead to this basically to this expression here, where we again would have something like the sum over the various Shannon entropies with respect to the different molecular sizes, and then again something in addition here, some additional term. So what does this mean for the thermodynamics of the system? This means that we again can compute the expected. So now we make things a little bit more concrete. We say each state Sij has some energy and energy state, and the internal energy simply then would be again the expectation value of these energies. And what would be the functional now that we maximize. So what we maximize now is the entropy. And in addition to that, we have a normalization constraint, which looks a little bit different because what we are normalizing is the total number. What we are keeping constant is the total number.
Rudolf, just to let you know, you're now in your question and answer period.
Okay, so I will just jump to the end quite briefly. So what we see is we have the internal energy. We get a little bit more complicated functional, and we get a distribution function that is now not a pure exponential anymore. And if we now look at the entropy, we see that the total number of molecules here, which is this term, plays a crucial role. And just to, I will simply jump to the end. So one can compute, of course, then entropy production, which again includes this molecular term here as the number of molecules and which arises here. So what we get is more or less a transition from microcanonical, from a microcanonical ensemble to something that is already almost so we jump to we could relate this to a chemical potential. So here I will stop.